And I'm a member of Barron's Lab in Tübingen. And today I'm going to talk about our recent work, which is also on uncertain estimation in deep neural networks. And let's begin. This one. Yeah. So I'd like to start with this collection of papers on the successes of deep learning. You probably know most of them, because some of them made a big splash when they were published. And the reason I picked these papers is that when they develop a deep neural network, they compare it with physicians or the current method in practice. And in the end, they conclude that deep learning is really, really effective. And one thing they are missing in their evaluation is uncertainty. Because when they make those comparisons, they evaluate their methods based on certain accuracy metrics like sensitivity, specificity, or like a ROC curves, area under the curve scores, and those kind of things. But nobody considered uncertainty in their evaluation. And given the successes of these papers, I think we should really, really consider uncertainty to go further. Because if you talk to a medical expert or physician, uncertainty is a big thing for them, because they want to make sure that their decision is correct, because they're making life and death decisions. So that's one thing that is really important in medicine. So, okay, so what is uncertainty in deep neural networks? Thanks to the previous speaker, you know all the details, all the equations, and all the definitions. But my approach is more visual. So if we have such a neural network, we train it, and we come up with a useful configuration of the parameters. And we make predictions based on those parameters. And since we work with finite training data, we don't know all the details. We don't know everything about the parameters. And in the end, we will have some kind of uncertainty in our predictions. And if you consider this predictive uncertainty measured at the output of the network, we can divide it into two categories. The first one is the epistemic uncertainty. It's because of our ignorance about the model parameters. And the other one is the aleatoric uncertainty. And this is due to the input noise, or the sensor noise, or motion noise. So it's because of the variation in the inputs. And you can also further divide it into homoscedastic and heteroscedastic categories. And if you're modeling assumptions, if you assume the constant variance or constant uncertainty for different inputs, that means you're dealing with homoscedastic uncertainty. And if you assume different levels or different variance for different inputs, different uncertainties for different inputs, you are dealing with the heteroscedastic uncertainty. And of course, there are certain methods to tackle the uncertainties in deep neural networks. So notable examples are the Monte Carlo dropout. So this is about estimating the epistemic uncertainty. And the key point is to use dropout at the test time. So when you randomly turn on and off your neurons, and you make multiple predictions for a test case, you obtain a predictive distributions, then you can evaluate your uncertainty levels. And similarly, this one is more recent compared to Monte Carlo dropout. This is also estimating epistemic uncertainty, but it's using the stochasticity in mini batches. And these are all approximate Bayesian methods. And if you don't want to take a Bayesian approach, you can also follow an ensemble approach. So if you train multiple networks, you readily have multiple predictions, and then you can use that distribution for uncertainty evaluation. And in this remarkable paper, they also combined the ensemble approach with the adversarial examples. And adversarial examples are kind of like augmented examples, augmented versions of the original examples. And by doing that, they obtain smoother distributions, and it works well in the end. And in a recent paper by Alex Kendall and Yarengal, they came up with a unified framework for estimating both types of uncertainties. And they say that if you are working in the regime of big data, you should focus on aleatoric uncertainty. Because if you have enough data, your epistemic uncertainty will be explained away, and you will be alone with the aleatoric uncertainty, right? That will be the more dominant component of your predictive uncertainty. So after reading those papers, I decided to focus on the aleatoric uncertainty, and I tackled it with this simple, nice, and easy method. So we are using the simple data augmentation methods at test time, and we generate T number of variations of the original input, and in the end, we are trying to estimate the heteroscedastic aleatoric uncertainty, because we are doing the same thing for each and every input, and in the end, we get different uncertainty estimations. And these are the operations in our data augmentation pipeline. They can be found in any deep learning framework. And basically, we are taking random crops of the original image and resizing it to the original size. Then we manipulate the brightness, hue, saturation, and contrast. Then we randomly flip it horizontally or vertically, and we apply a random rotation. So it's as simple as that. So nothing else, nothing more. And to test our idea, to test our hypothesis, we are working on a diabetic retinopathy detection data set. So this data set was released in 2015. It came from a Kaggle competition, but it's a nice data set to work with and try different things. So DR detection is a challenging or important task, because global incidence rates are increasing and manual detection is time consuming. So it's a good idea to automate this task. And FDA has recently approved the use of deep learning based method, and I think it was in April. But I don't think they had this uncertainty business in their approach. So it might be a next step. And in this data set, we have 5 different categories depending on the disease levels. So, and most of our data set comes from the healthy patients. So we have a huge class imbalance. And in addition to these 5 categories, we introduced 2 additional binary classification tasks by dividing this disease continuum into two levels. And in the first case, we set this one as a threshold, so it becomes a disease onset level 1, and we try to make a prediction for 0 versus others. And if we set the disease onset level to 2, we make such a separation. And that's the basic problem specification. And to solve this task, we used a convolutional neural network based on the original ResNet architecture. But in addition to the basic architecture, we followed their design principles, but we made our own design choices. You can find the full specification in the paper. And we trained this network with Adam in an end-to-end fashion, and we run it for 1 million iterations. And in order to account for the class imbalance, in the early phases of training, we use a balanced mini-batch, and then we increase the mini-batch size to 8, and we use stratified mini-batches. But if you consider those class ratios, even this one is introducing an oversampling of the minority classes. And in the end, we trained this network with more than 7 million images generated on the fly. And during the training, we validate the model once in 10,000 iterations, and we pick the best model. Then we use it for inference. And when we generate variations during the test time, we generate 128 variations, and we make a decision based on the median prediction, and we evaluate the uncertainties with respect to interquartile range. So everything is pretty straightforward. And you can find all the details about our network at this link. And if you have questions, if you have in support for our code or anything, feel free to contact us. And let's see how the network performed. So on the left, we see the training curves for our networks. And the red curve is showing you the full-blown training curve. If you look at it, it may fool you that the network converged well, but if you skip first 10,000 iterations, you see that there is room for improvement. So network has not converged, but we decided to go with it because it was close to our reference points. So in an earlier study, the Leivik et al. Used the same data set, tackled the same problem, and they estimated the uncertainties based on the Monte Carlo dropout. So that was our reference performance. Their results were important for us. And since we are close to them, we decided to use this network for our uncertainty business. And when we did that, we got such lovely plots. So we are estimating the uncertainties for our individual data points, and we decided to see if there is a difference between correct and misclassifications. So if there is such a difference, maybe we can use that information to do additional things, right? So on the left-hand side, we see the distribution of uncertainty estimates divided into correct and misclassifications. And on the right-hand side, we see the similar plot for the onset level 2 scenario. And we see that in the case of misclassification, uncertainty is higher. And we want to use that information for a clinical purpose. And we came up with this uncertainty-informed decision referral scenario. So in a clinical setting, if your network is telling you that there's a high uncertainty about this prediction, maybe you should refer that patient to a real physician, right? Instead of automatically deciding on that case, you should refer that patient for further evaluation. So that's, by doing that, we mimic a clinical workflow. And in this plot, at the bottom, we see really nice curves. So at this point, we don't refer any patients, right? And if you rank our predictions based on their uncertainty estimates, and if you refer top 10%, top 20%, top 30%, and we get to the right-hand side of this figure, and if you refer patients for further evaluation by a physician, we obtain monotonic increase in the remaining cases. So uncertainty estimates obtained by our method are useful. We can use it for decision referral. So that's a good thing. And it shows that our method is providing useful uncertainty estimates despite its simplicity. And after submitting my paper, after we got the reviews, one of the reviewers asked for representative cases. So these figures are not in the paper, but I would like to share it with you at the conference. So we looked into the decisions made by the network and the uncertainties obtained by our method. So over here, I'm presenting 1 minute, okay. Okay, I'll be quick. So we can use these uncertainty estimates for error correction. So this is a healthy case, and in the case of binary classification, single prediction is wrong. But if you make multiple predictions based on variations of this input, we get this median prediction, and it's 0.4937. So it's marginally below the threshold, and we can recover from this misclassification by generating multiple copies of the instance. And such a tight decision is also, like I said, the danger of such a tight decision is also indicated by the high uncertainty level, right? So there is a high uncertainty, and it's a dangerous decision, so be aware of that. And in another case, we can use such uncertainty estimates for relabeling. And if you look at this figure, so this is a moderate DR example, and all the networks are predicting it as a diseased case in the case of binary classification. And if you separate those probabilities into 5A classification, we see that our network's predictions are pretty consistent, that it predicts class 3 instead of the given label, right? So after getting this, I was kind of suspicious about the label, and I contacted a real physician in our institute, and I asked him to label this case, and he said I would assign class 3 with a tendency towards 4. So, and I think it's consistent with our network, so we can use such uncertainty estimates to relabel the instances. And I also used the information gain to separate aleatoric uncertainty from epistemic uncertainty, but I don't think we have time for this one, so if you're interested, we can talk offline. And let me conclude. So we used a simple data augmentation pipeline to estimate the predictive uncertainties. It's as simple as it sounds, and it's a general approach. It can be used with any network, any architecture, and by doing that, we estimated the heteroscedastic uncertainty of deep neural networks, and we showed that it's useful in a clinical setting, or at least when you mimic such a clinical scenario. And we want to continue this work by analyzing more advanced data augmentation pipelines, and we want to create ensembles of such networks to get a better idea of all those uncertainties. And in the end, we want to come up with a systematic way of relabeling and error correction. So thanks for listening, and I'm happy to answer your questions. And that's the lovely Tübingen.
Okay, thank you. We have time for a few questions. Are there questions from the audience?
Thanks for your presentation. With the uncertainty measurements, they're going to depend on the amount of augmentation you do to your images at test time. So if you don't apply much deformation, the uncertainty will come out as very small, and otherwise it might be bigger. So A, how do you choose the correct amount of deformation to apply? And B, how does that play into the amount of augmentation you're doing at training time?
Actually, that's a good question. And I think, first of all, I used a large range for this data augmentation pipeline. I mean, the large range for the data augmentation parameters, they are random parameters. And I think I used relatively large range of parameters for those functions. And that's one of the reasons, I guess, it took so long for convergence. If you use a narrower range of parameters for data augmentation, it should take less iterations to train the network, but then, of course, it will impact these uncertainties. Because when you use a larger range of parameters for data augmentation, you create more variations, right? You cover a larger area in your input space. Yeah, but I think that's one of the things we need to try to understand this thing better. That's on our agenda.
Okay, and we have time for one more question.
Yeah, very interesting work. But of course it's quite costly because you have to do over 100 classifications with these augmented data in order to come at this estimate of uncertainty. What if you just train a second network that takes the output of the first network and the image and tries to predict if this is an image that you should send through to the human reader, like you showed in your graph? Is that a much simpler approach, which would be much more powerful because then you're really training a network to do the task you're interested in?
Actually, first of all, 128, it seems large, but maybe you can get a similar performance if you try smaller numbers. I didn't try different numbers. I just used 128, and it worked well. And what you said is also reasonable, but I think you need to come up with labels for that kind of decision. And I think it takes more evaluation and more thinking. So I didn't think about that, but it might be a useful approach. So thanks for the suggestion. So.
Okay, let's thank all the speakers one more time. And let's move on to the poster session right now.